Okay, so we'll start off with just a little brief review. So last time we learned, we continued normal and tangential coordinates, and then we went and looked at radial and transverse. I apologize for that screen. I do not know how to fix it. I tried before classes start to get that to work properly. I could not. But nevertheless, we looked at radial and transverse components. These are also known as polar, or if you're working in 3D, you'll be using cylindrical coordinates. In that case, you just have, as shown here, you would have another unit vector pointing out of the page, and it would simply be a k vector. It would be fixed such that it doesn't change with time. So we showed that the position vector r here is equal to, well, some scalar function r of t in the e hat r direction. And that is always true because in this coordinate system, it is rotating or moving as the particle moves as well. And then the second unit vector we saw was the e hat theta, and we just wrote down that they were normal to each other by definition. Okay. We went through and computed the velocity shown here, and we ended up needing to take a time derivative of e hat r because it is moving or rotating specifically. And then we end up with this extra term, this r times theta dot in the e hat theta direction. We then went and differentiated that again and had to take time derivatives of both e hat r and e hat theta, and we got this more complex term for the acceleration shown here with components in both directions. Okay, so we did a pendulum. We then did this particle moving along this specified path. And then today we're going to consider a pendulum in 3D with an elastic wire or an elastic spring connecting it. And we're given the unstretched length of the spring in this case, which is just h squared plus a squared plus b squared. And you can say then that the r0 position is a squared plus b squared. And we're asked to determine the position when theta of t is an unknown degree of freedom, and when we prescribe the rotation of this pendulum as omega t, meaning that it's rotating with a constant angular velocity omega. Okay. So we're going to start by choosing a coordinate system. So definitely you're going to need radial and transverse in order to describe the rotation of this pendulum. And then we're going to need a third degree of freedom, or third coordinate, or third direction to describe the vertical height. And so in this case, we're going to end up using cylindrical, which, like I've said before, is radial and transverse plus an additional Cartesian direction in the vertical direction. So we'll say that we're going to use a cylindrical coordinates, and we can put the origin anywhere we want, but a convenient place is to put it where that spring is anchored to the ground. So we're going to say cylindrical with origin at the location where the pendulum is anchored, or we can say where the spring connects to the ground. So in this coordinate system, we're going to put our e hat r direction in the direction of that mass, sitting in a horizontal plane. This is e hat r. We'll have e hat theta over here, and then we're going to have a third coordinate, which will be our k direction, k hat, or you could choose e sub z, whatever you want. And then given this coordinate system, we're going to have that counterclockwise rotation is positive. And in this case, that rotation is about the k-axis. Okay, so this r0 squared term, this is the unstretched length of that spring projected into the e hat r direction. That's what we're going to use it for. So we'll just write it down here so I don't have to scroll back up. So this is equal to square root a squared plus b squared. And then we can write that our position vector, well, we're going to first draw it starting from the origin to our mass. to our particle. That is our position vector. It's going to have two sets of components here, one in the E hat r direction, one in the k direction. And so for r, we're going to get rt, vector r of t is equal to the quantity. So when I say quantity, I just mean stuff inside parentheses. That's what I mean. So if I say quantity squared, I mean everything inside the parentheses squared. So in this case, we have the quantity of rt plus r0. And here's where that r0 shows up. All of that in the E hat r direction. And we're going to have another coordinate in the k direction. So the unstretched length, in fact, this is going to be not plus, this is going to be minus because we're going down. K direction points positive up, and our pendulum as drawn is downward, so we're going to have minus. In this case, we're going to have h, and that's our position of static equilibrium, or where the spring is unstretched, let's say. That's what we're measuring it from. Let me back up. It's not static equilibrium. It's the position where the spring is unstretched, which is not equivalent to static equilibrium in this case. So we've got h, and then we need a vertical coordinate. We're going to use z, so we'll have z of t here, and all of that in the k hat direction. So that is our position vector here. Any questions on that position vector? All right, in that case, we're going to move on. We're going to compute the velocity and acceleration vectors. We're just going to take time derivatives here. So we're going to start with r dot. R dot of t is equal to, first we'll take the derivative of what's inside the parentheses, and r0 is a constant, so we'll just get r dot E hat r plus r0 times E hat r dot plus z dot, because h is a constant, z dot k hat plus z k hat dot. Now what is k hat dot?
Wouldn't it just be zero since our k hat isn't changing?
Yeah, so k hat dot is 0 because our k hat vector is never changing. All of the rotation is happening about that, so the E hat r and E hat theta are changing, but k hat is not changing. So this right here is 0, and then last time we saw that this quantity here is theta dot E hat theta, such that our velocity vector r dot of t is equal to r dot E hat r plus r0 times theta dot E hat theta plus z dot k hat. Okay. Yeah.
Why is the derivative of E hat or E hat theta dot E hat?
Sure. Yeah, that is, so the question is, for the recording, the question is, why is E hat r dot equal to theta dot E hat theta? That's something we actually went through last time. We went through a derivation of that. Let me scroll back up here. You can show it right here using the chain rule. And so you should have that in your notes, and I recommend you review it, although in practice you're just going to end up using these formulas for the r dot and r double dot, and then you'll end up plugging things in based on what you know about the problem. You can do the same thing with the E hat theta dot as well. I don't think we showed that here. That's something you would prove in like an advanced dynamics class as like a graduate student, I would say. Okay. Any other questions? Yeah.
What happened to the negative sign? That was in the...
Yeah, that's a great question. It fell out because in my notes I have a positive sign and my notes are wrong. So just keep correcting me in that. So yeah, it should be minus z dot k. All right, so we'll go ahead and compute the acceleration. That was our velocity. For acceleration, we're going to just take another time derivative. We're going to consistently just take time derivatives. And first term, we're going to get r double dot plus r dot, I left out the unit vector e hat r. So r double dot times e hat r plus r dot e hat r dot plus r dot theta dot e hat theta. This comes from taking the derivative of the first term up there. Derivative of r plus r0. R0 is constant, so we just get r dot. So r dot times theta dot in the e hat theta direction. We're going to need to do product rules here. So we'll then get plus r0 theta double dot e hat theta plus r plus r0 theta dot e hat theta dot minus z double dot k hat, and we don't need to do k hat dot because we know that's 0 because k hat's constant. Okay, so we just saw that this e hat r is theta dot e hat theta. You can show similarly that this e hat theta dot, this term is equal to, actually in this case it becomes minus theta dot e hat r. In this case, a minus sign pops out, which is different than when you do take the derivative of e hat r. Okay, so from here we're going to group up terms, and we're going to get that our acceleration vector r double dot is equal to r scalar double dot minus the quantity r plus r0 times theta double dot. And all of that is in the e hat r direction plus the quantity r plus r0 times theta double dot plus 2r dot theta dot in the e hat theta direction minus z double dot in the k hat direction. And just as an aside, you can actually eliminate this r0 from this as well. If you do, you say let big R equal to r plus r0, then you'll find that big R dot is equal to r dot, and big R double dot is equal to r double dot. And then you'll find that in this case, the acceleration vector of t will be equal to big R double dot minus big R theta double. Wait, hold on a second. This term right here is not correct. That should be a theta dot squared term. And my notes are not right. Let me fix that. So that term comes from over here, where we've already got a theta dot, and then we get another theta dot and a minus sign, so we should have theta dot squared. And that ends up in the e hat r direction, so that's what this term should be. And then everything else looks correct. So coming back here, we should have theta dot squared in the e hat r direction plus r big R theta double dot plus 2 big R dot theta dot in the e hat theta direction minus c double dot in the k hat direction. That's just to show you that you can define a variable that really just measures the stretch in the spring rather than the total length of the spring. And then you can define the acceleration, and then if you go do like Newton's second law or something, you can find an equation of motion for this pendulum that depends only on on the stretch in the spring rather than the stretch in the spring and the rotation, but rather than the total length. Okay, but we were asked to determine the acceleration when theta is an unknown degree of freedom and when it's prescribed or the angular velocity is constant. So for A, this is where theta of t is unknown. And in this case, we're just going to get what we already have. We'll get r double dot equal to the quantity r double dot minus r plus r0, theta dot squared, all of that in the e hat r direction, plus quantity r plus r0, theta double dot, plus 2 r dot theta dot, e hat theta direction, minus c double dot k hat. That is our answer for part A. And you should note that there are 3 unknowns here. So we'll just say note that there are 3 unknowns. Which are r of t, theta of t, and z of t, and their derivatives as necessary. But if you know those 3, then you can find their derivatives. Yeah.
So when we did the e hat dot in the theta direction, the derivative of that is always negative theta dot e hat r.
Yeah, that is true, period.
And the derivative of e hat r, or e hat dot r is theta dot e hat theta.
Yeah. So this relationship is always true, period. There's never a situation where it's not true. Given this coordinate system, and this expression here, that is always also true. And you can prove this. We are not going to do the proof, but it is possible to prove this. So undeniably true always. Any other questions? Okay, then we're going to go on to B. So in this case, we are told that theta of t is equal to omega t, which then implies that we have a prescribed motion. Oops. Meaning, in other words, that there is something causing this pendulum to rotate with a constant speed. Some external moment is being applied to force that to happen. And as a result, we end up with reducing the number of unknowns by 1. So we can say the number of unknowns is reduced by 1 because we now know what theta is. Of course, there would be some moment driving this, and so you could ask, well, what is the moment required in order to force this to occur? In this context, we're not going to worry about that right now. So if we know that theta of t is equal to omega t, we can then go and find theta dot. Taking derivative of that, we'll find here that theta dot is equal to omega, so we have a constant angular velocity. If we take another time derivative of that, we'll get theta double dot is equal to 0, such that there is no angular acceleration being imposed here. And then we can take what we see in A and we can just substitute in the values there. and we'll end up finding here that r double dot is equal to r scalar double dot minus r plus r0 omega squared, the e hat r direction, plus, in this case we'll have 2 omega r dot, and that's everything in the theta, e hat theta direction, minus still z double dot k hat. And that is our solution here. Oh, oops. So I just want to briefly say that this term right here, with this omega squared term there, that ends up acting like a pseudo force. And if you've ever heard of like centrifugal forces, this is what causes that, is this rotation. In general, it's easier, in my opinion, to deal with this in the kinematics and find these types of pseudo forces through the acceleration term rather than making an assumption of what that pseudo force is. The kinematics is very logical, very systematic, and it will give you all of the terms you need rather than having to make guesses about what like a centrifugal or centripetal force is on this system. Okay, and so in this case, we now only have 2 unknowns. And our unknowns are going to be still r of t and z of t. And then if you were to solve and use the e hat theta term in terms of like using Newton's second law, you would end up being able to find the moment that's being applied to force this with a constant angular velocity. Okay, any questions on this example before we go through just a summary of all the coordinate systems? All right. Okay, in that case, we're just going to go through just a table of the different coordinate systems. We're going to write out what their coordinates, unit vectors, position vector, velocity vector, and acceleration vectors are, just so you have it all in one place. And I will say that the radial and transverse also extends to cylindrical. You just add in a k hat unit vector, and then you've got cylindrical. There are other coordinate systems, such as like spherical, for example, but we won't cover them right now. All right, so in Cartesian, we're just going to use x, y. If we want to extend this to, it says 2D, but you could extend this to 3D, and then you'd have a z as well. We'd have I hat, j hat, and we'll just add in k hat for 3D. Our position vector is simply going to be equal to some x component in the I direction plus a y component in the j direction, then plus a z component in the k direction. We then take simple derivatives of that. We'll get r dot is equal to x dot I plus y dot j. That being said, x and y don't necessarily have to be simple. They could be some complex expression given the motion of the system. The point here is that everything in the I direction, you're going to take a derivative of that. And you don't take derivatives of the unit vectors in this coordinate system because they're all fixed. So r double dot here is then just x double dot in the I direction plus y double dot in the j direction, and then you'd have a z double dot for 3D. Okay. So I guess we'll just go in order. So radial and transverse or polar, we have r and theta. Those are our primary coordinates. In cylindrical, you're going to add in a third one, z, like we just did with this elastic pendulum. Our unit vectors are going to be e hat r, e hat theta, and then you could add one in there. Our position vector is r equal to r in the e hat r direction. And again, that r could be a complex expression. It doesn't have to just be r. It will depend on the system that you're analyzing. For the velocity vector, we're going to have r dot is equal to scalar r dot e hat r plus r theta dot e hat theta. That is always true. For our acceleration, we have the vector r double dot is equal to the quantity r double dot minus r theta dot squared in the e hat r direction plus the quantity r theta double dot plus 2 r dot theta dot in the e hat theta direction. For normal and tangential, our coordinate is going to be the arc length, or S. Unit vectors are e hat t for the tangential direction and e hat n for the normal direction. And I'll give you a moment to catch up, and then I'll ask you a question. Okay, so what was the position vector in normal and tangential coordinates? It doesn't exist. It doesn't make sense to ask that question given that the coordinate system is fixed and attached to the particle as it moves. So there is no position vector. But there is a velocity vector, and the velocity vector is actually equal to the arc length dot, or just equal to the speed, which we'll use a script v e hat t, because this coordinate system is defined based on the velocity of the particle. And the e hat t direction points in the direction of the velocity by definition. And we also said last time that the velocity vector can only ever be positive because we've defined our coordinate system based on that. We never have a negative velocity in this coordinate system because that also just doesn't make any sense. That doesn't mean you couldn't define a coordinate system based on the negative velocity. It wouldn't be this coordinate system, it would be something else, because then your normal vector would be pointing in a different direction. All right, so in this case, the acceleration vector, we're just going to use a here. We're not going to use r double dot because there's no position vector, so it doesn't make sense to use r double dot. If you use r double dot, that implies that there's a quantity r that exists, which is not true in this coordinate system. So we're just going to use a here. You could use v dot, that would be fine, but no r double dots. And this is going to be that derivative of the speed, e hat t, plus the speed squared over rho, which is the radius of curvature, in the e hat n direction. Okay, any final questions before we go to the worksheet? All right.